In this class, we will go over the previous UTME past questions. You will find useful tips and tricks along the correct answers and solutions for all the physics questions. Like always, we will be using the ExamGuide app. You can download and practice more questions using this app. Let's get started. Now, we have the first question, which is the easiest. What is the subject? What subject is this? And that is physics. So we go to the next one. It said, what is the least possible error encountered when using or when taking measurement with a meter rule? So when you are using a meter rule, if you know that a meter rule starts from 0 and then extends to 100, and that is why 100 in centimeter, remember, and that is why we call it a meter rule, because 100 centimeter makes one meter. Now, if this is the 0 point, then we now have 5 times to get to 1. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is 1, okay? Now, that means each of them means 10 millimeter. So if you have 10 millimeter is equal to 1 centimeter. And then it means that 1 millimeter is going to be 1 divided by 10. Okay, so what this is telling us now is that for each millimeter, you are going to be recording in 0.1 of a centimeter, all right? So from here, from this 0 mark to the first division, you have 1 centimeter. I mean, from this first part to this first division, which is 1 millimeter, because 10 of them will give you 1 centimeter. So in order to get the uncertainty, or that is the least possible values, you have to divide it by 2, right? So when you divide this by 2, you now have 0.5 millimeter. And that is going to be the answer, because each one now is 1 millimeter, 2 millimeter, 3 millimeter, 4 millimeter, 5, until you get to this one, which is 10 millimeter, which makes 1 centimeter. So the option there is going to be 0.5 millimeter and not 2, 0.2, 9, not even 0.1 or 1 millimeter. So the option is A. A quantity which requires magnitude and direction to be specified is, now, when we talk about quantity and magnitude and direction, we are talking about a vector. So we are going to consider which of these options is a vector. Distance is not a vector, neither does temperature or mass. The only vector we have here is displacement, and that is option A. Now, we also have this question, say electrical potential, torque, kinetic energy, and momentum. Which of the quantities listed below are vectors? Now, electric potential talks about the energy, so it's not going to be a vector. Torque is a force, so it's a force that brings about rotation. So torque is going to be a vector. And kinetic energy is also not a vector. Now, momentum is a vector. So the options here are 2 and 4, and that is option C. Which type of motion do the wheels of a moving car undergo? When a car is moving, 2 things are happening. The wheels are rotating, and it is moving from one point to the other. So we are going to choose rotational, and oscillation is not the option. Translational and rotational. Vibratory and translational. Random and translational. So a car does not go in a random motion. A car does not vibrate while it's moving. So the option is B, which is translational and rotational. Now, looking at this graph, from the diagram above, the region of 0 acceleration is. So when you have a velocity time graph, if you have a velocity time graph, v meters per second, and then t in seconds, every value you see on the vertical is for velocity, and any value you see on the horizontal is for time. Now, whenever a body is in this direction, we say that the body is accelerating. And whenever a body is in this direction, we say the body is at constant velocity. So this is constant velocity, and this is acceleration. So whenever a velocity is constant, we now say that there is no acceleration. So for us to be able to find a point where there is zero acceleration, then it should be from n to s, because at that point the body is at constant velocity, and constant velocity simply means zero acceleration, and the value is a, not sp. When we talk about sp is acceleration, pq is deceleration, mx, so there is no mx there, so the option is ns, which is zero acceleration. A car accelerates uniformly from rest at 2 meters per second. Okay. A body accelerates uniformly from rest at 2 meters per second. Its velocity after traveling a distance of 24 meters is, all right, a car accelerates uniformly from rest. So when we say that a body started from rest, it simply means that initial velocity of the body is 0. And then at 3 meters per second square, whenever you see meters per second square, you know it's acceleration. Okay, so A is acceleration, which is 3 meters per second square. And its velocity, that is, we are looking at the final velocity when it goes a distance of 24 meters, okay? At this point, such a formula for equation of motion to apply here is going to be v squared equal to u squared plus 2as, right? Because this is the formula to use to find a final velocity when a body starts from rest. So this is the formula. We are not using g because the body is not thrown from up. So it's not talking about a motion of a body under gravity. So this v is going to be square root of u is 0. So when u is 0 is not part of it. So you have 2 times acceleration is 3 times s is 24. So this is going to be that v is going to be 6 times 24 in a square root, and that is going to be 6 times 24 is 144. So when we have square root of 144, so v is going to be 12 meters per second. So a car accelerates uniformly from rest, not 72. So 12 meters per second is option C. Now calculate the escape velocity of a satellite launched from the Earth's surface if the radius of the Earth is 6.4 times 10 raised to the power 6 meters, and take g as 10 meters per second square. Now, if a body is moving like a satellite, let's assume this is the Earth, and then the satellite will be revolving around the Earth at this point. So the major thing we need to do there is that the walk taken is the force times distance. So when you want to find the escape velocity, you apply this principle, 2g capital R, because this is the formula for escape velocity at this point, because what is involved there is that the radius of the Earth is there and the acceleration due to gravity. So using this formula, we now have that v is equal to square root of 2 times 10 times 6 times 10 raised to the power 6. And so this is going to be 60 times 2 is 120 times 10 raised to the power 6. So I'm going to have square root of 120 square root of 120 is 10 10.9, 10.1. So I'm going to have 10.1 times 10 raised to the power 6 times 1 over 2. Because I have to raise this square root to a power of 1 over 2 such that this will cancel this. I have 3. So this is V is equal to 10.1 times 10 raised to the power 3. So G times this. So in that case, we don't have 10 there. Let's recheck our process. Okay, 6.4, not 6. So this is going to be 6.4, not 6. 6.4 times 10 raised to the power 6. Therefore, I'm going to say that V is equal to 6.4, 10 times 6.4, so 128. So square root of 128 is 11.3. So 11.3 times 10 raised to the power 6 times 1 over 2. So V is 11.3 times 10 raised to the power 3. This is meters per second. So, but then at this point, we have 11.3 there, and I'm sure this is the option. But in this case, they have capital K. When you see capital K, it means 1,000 or 10 raised to the power minus 10 raised to the power 3. So what we are going to do here is we are going to say 11.3 K. Instead of 10 raised to the power 3, we're putting K and meters per second. And that is option B. An object of weight 80 kilogram on Earth is taken to another planet where the acceleration due to gravity is 1/3 of its value on Earth. The weight of the object on the planet is. So at this point, on Earth, G is given as 10 meters per second. Now, another planet, G is 1/3 times 10. Therefore, in that planet, we have 10/3 meters per second square, please, second square. Now, they say find the weight of the object at that planet. So the weight is going to be on that planet. So I'm going to call it WP for the planet, where we have mg. So this is going to be mass is 80. Mass does not change irrespective of the planet. Then times acceleration due to gravity has changed. Instead of g, I'm going to put, so I'm putting this gp. That is acceleration due to gravity in a given planet. So this is going to be 10/3. And acceleration due to gravity is 80 times 10, that's 800 divided by 3. So 2627. So apparently the option is going to be 1/3 of its value. Yes, it's going to be 27. Because, yes, you are going to assume that it's 27 because at this point I have 266.7. So apparently the option was expected to be the weight of the planet on that place is going to be 266.7. I'm sure that may be a mistake of the option, so it should have been, it should be 267 Newton. So that is going to be the value, and I'm using option A as that because this G is supposed to be 80. If it's supposed to be 8, so if I use 8 instead of 80, if I use 8 here instead of 80, then I will have that option as option A. So moving on. One of the conditions necessary for an object to be in an equilibrium when acted upon by number of parallel forces is that the vector sum of the forces is. Now, the conditions necessary for an object to be in an equilibrium. If you watch some of our videos, you see this topic is well treated. So for a body to be in an equilibrium, so the sum of forces acting on the body must be 0. And that means the body is not accelerating. So that is why the sum of the forces is going to be 0. So the option is D. It cannot be negative. Neither will it be positive. It's not average, so it's 0. Now, when you say, what happens when 3 coplanar non-parallel forces are in equilibrium? When we talk about coplanar non-parallel, we are talking about, let's assume this is an object. A force is acting on its part, we call it F1, and probably another force is acting on this part, let's call it F2. So we now say that we have a coplanar force, and then maybe there is another force, probably the weight of the object, acting on this part. Now, if you check very well, the direction of these forces must have a point of meeting, or a meeting point. So when they all intersect, let's assume that in a free body diagram, I'm going to have this, this, and this. So you see, all of them have made a meeting point, or a point of intersection of all the forces. So when that happens, we say we have a coplanar non-parallel forces. I said the options, they say they are represented in direction only. No. The lines of action meet at a point. Yes. According to our explanation, this is what it is. This is the answer. The lines of action meet at a point. No. Yes, which is correct. The lines of action is parallel. No. They are represented in magnitude. No. So the option is B. An object of mass 20 kilogram is released from a height of 10 meters above the ground level. The kinetic energy of the object just before it hits the ground is. So let's assume this is a height, 10 meters. Big, this is the body, 20 kilograms. So it is released to be falling. As it is falling down, we want to find the velocity, the kinetic energy, as this body is just before it hits the ground. Kinetic energy of the object just before it hits the ground. Okay. In this case, we know that the kinetic energy of the body is given as half mv squared. Then we know that we already have the mass of the body times the mass is 20. What we don't have is the velocity. Now remember that whenever a body is released from a height, the best formula of motion is given as v squared is equal to u squared plus 2gh. Remember, I'm using g now because gravity is involved. So in this case, it is started from rest. Therefore, u is going to be 0. Therefore, I'm having v squared is going to be 2 times 10 times 10. 10 is acceleration due to gravity. So this is going to be 2,000. And that is v squared. So I don't want to take square root because v squared is already here. So all I do is remove this v squared and replace it with 2,000. So this is going to be kinetic energy is going to be 1 over 2 times 20 times 2 zeros. Yes, this is 200. Then this cancels this, I have 10. So kinetic energy is going to be 2000 joules. So 2,000 joules, and that is option A. Now, the energy in the nucleus of atom produce heat. Produce heat which can be used to generate. All right, the energy in the nucleus of an atom produce heat. Okay, heat energy can produce mechanical energy, and heat energy can also produce electrical energy. So the two of them. Okay, remember that energy can neither be created nor destroyed, but can be converted from one form to the other. So any form of energy, but For in the context of this question, we choose electricity, from heat energy to electricity. Mechanical energy also is there. Okay, option A. A machine whose efficiency is 75% is used to lift a load of 1000 Newton. Calculate the effort put into the machine if it has a velocity ratio of 4. The general formula of efficiency is given as mechanical advantage all over velocity ratio times 100 all over 1. Now, when we talk about velocity ratio is already given as 4, and mechanical advantage is load over effort. So let's substitute this into this equation. Efficiency is already given as 75%, so I'm going to have 75 over 100, which is equal to. Mechanical advantage is going to be load over effort. The load there is 1000, so I'm going to have 1000 all over effort times 4. I'm not going to multiply by 100 because the 100 is already here. It's either I remove the 100 here, I will now multiply by 100, or I will remove the 100 here, I will have it dividing here. So I think I'll prefer this one. So this is going to be 4 itself 1, 4 into 100 is 25. So I have, this implies 75 over 100 is equal to 250 over E. That is over the effort. So this is 75 effort is going to be 250, 0, 0. So effort is going to be 25,000 divided by 75. 25,000 divided by 75. So I have 3.33.3, and that is going to be Newton. Yes. So it's going to be 33.3, and that is option A. Number 15, a wheel and axle is used to raise a load whose weight is 800 Newton when an effort of 250 Newton is applied. If the radii of the wheel and that of axle are 800 millimeter and 200 millimeter respectively, the efficiency of the machine is. So we are still on the formula for efficiency, and this is still the general formula of efficiency. So what we are going to do is model this formula depending on the question we have. But they say that the wheel and axle, whenever you have the wheel and axle, the velocity ratio is always bigger radius all over small radius, and bigger radius there is 800 millimeter, and smaller radius is 200 millimeter. And remember, when they cancel each other, we have 4, and they don't have units because the units are cancelled. So that is my velocity ratio. So what is my mechanical advantage? Now the weight is 800 Newton and the effort is 25. So mechanical advantage is also load over effort, and the load is 800 and the effort is 250. So when the two of them divide, 800 divided by 250, I'll have 3.2. So this is 3.2. Therefore, I will substitute these values in this expression. So I have that efficiency is, where I have mechanical advantage, I'm putting 3.2 all over velocity ratio, I will put 4, then times 100. Divide by 4. So this is 80. 80 is the answer. The option is D. Now, a force of 500 Newton is applied to a steel wire of cross-sectional area 0.2 meters square. The tensile stress is, all right. When we talk about tensile stress, you are talking about a kind of pressure. So the tensile stress is given as force over unit area, and the force there is 500 divided by 0.2. So tensile stress is given as 500 divided by 2. It's about 2. Yes, because this is going to be 500 divided by 2 over 10. And this is going to be 5,000 divided by 2, which is 2,500. And this is Newton per meter square. So 2,500, that is 2.5 times 10 raised to power 3 in standard form. From the graph above, the point that represents the elastic limit is the first length, which represents a kind of acceleration in a Newton, in a velocity time graph. So the first one is going to be between 0 and r. So at r, I have my elastic limit. A small droplet of water that form on the grass in the early hours of the morning is dew. It's not mist, it's not fog. So these are other classes of dew, but dew is that one which forms a droplet of water. Just like when you bring out water from the freezer. So the body, what you see in the body, a kind of droplet of water forming on the body when it is melting, is called dew. And that is the same thing that happens in early hours of the morning. What is the equivalent of 200 K in Celsius scale? 200 K in Celsius scale. We have that, this is the Kelvin scale, is going to be equal to degrees Celsius plus 273. So for me to find this, I'm going to, this T represents Kelvin. So I'm going to have 20 is equal to theta plus 273. So this is going to be theta is equal to 20 minus 273. So theta is going to be, it's just like saying 273 minus 20. This is 3, 5. So the answer is going to be negative 253 degrees Celsius. Okay, that is option D. Number 20, a glass bottle of initial volume 2 times 10 raised to power 4 cm cube is heated from 20 degrees Celsius to 50 degrees Celsius. If the linear expansivity of the glass is 9 times 10 raised to power minus 6 per Kelvin, the volume of the bottle at 50 degrees Celsius is. All right, this question is about, since they say I should find volume, we are going to be using cubic expansivity. And the cubic expansivity is the increase in volume per degree rise in temperature. Increase in volume per unit volume per degree rise in temperature. And that is going to be cubic expansivity, or it depends on, this is the symbol, it's given as V2 minus V1 all over V1 times change in temperature. And it is also noted that cubic expansivity is given as 3 times the linear expansivity. So for us to have a volume expansivity, we have to say 3 times the linear expansivity. And the linear expansivity is 9 times 10 raised to power minus 6 per Kelvin. So I'm going to say 3 times 9. Remember, this is 3. This is the linear expansivity. And this linear expansivity is 9 times 10 raised to power minus 6. And which is equal to? The question is, what are we looking for? What we are looking for is the volume at. That volume at 50 degrees is the volume after the expansion. So it is V2 we are looking for. V2 minus V1 is the first one, which is 2 times 10 raised to power 4 all over 2 times 10 raised to power 4 times the change in volume, the change in temperature means the higher temperature minus the lower temperature, and that is 50 minus 30. No, that is from 20 degrees Celsius to 50. So this 20 here is, so 50 minus 20 is going to give us 30. All right, we are going to clear the fraction. What I'm going to do is V2 minus 2 times 10 raised to power 4 is equal to this times this. 3 times 9 times 10 raised to power minus 6 times 2 times 10 raised to the power 4 times 3, 0. Then remember this negative value in this place will be added at this point in terms of balancing of this simple equation. So V2 is given as 3 times 9 is 27, times 2 is 54, times 30. Then so 3 times 9 times 2 times 30. That's how we do it. First, multiply the whole numbers, multiply them first. I have 1620, then times 10 raised to the power minus 6. Of course, remember this is going to be added 20,000 because 10 raised to the power 4 is 20,000. So V2 is going to be no. Remember this is another 10. 10 raised to the power 4 is here. 10 raised to the power 6 is here. So according to law of indices, when they are multiplying, their powers will add. So minus 6 plus 4 is minus 2. So minus 2 is something as dividing by 100. So 1620 divided by 100 is going to be 16.2 plus 20,000. We are going to have 16.2 here, which is going to be 20016.2 cm cube. So the option here that corresponds to the question here, the answer is C. Now the equation P raised to the power A, V raised to the power B, and T raised to the power C is equal to constant reduced to Charles' law if, according to Charles' law, the volume of a given mass of gas is directly proportional to the temperature if pressure is constant. Therefore, I will say that V1 over T1 is equal to constant. All right? Simply put, V all over T is equal to K at absolute temperature. Very importantly, is directly proportional to the absolute temperature. Now, the equation is P raised to the power A, V raised to the power B, and T raised to the power C is equal to, this same thing can be written in indices as V raised to the power 1 and T raised to the power minus 1, because the 1 divided is raised to the power minus 1. Then since there is no P, P is going to be 1, which is P raised to the power 0. Therefore, my A represents, this A is the same thing as this. So whatever is on top of A at this point is equal to the same thing on top, whatever is the power of P on this side of equation will be the same power of P on this side of equation. Therefore, if this is A, it's going to be equal to 0. The same thing applies here. B is going to be equal to 1. B is 1. And C is going to be equal to minus 1. So which of these options correspond to what I have here? So you have to be careful not to pick the wrong one. A is equal to 0. And B equal to 1, and C, no, not that one. B, A equal to 0, B equal to 1, and C equal to minus 1. Option B is the answer. Then C, A equal to 1, B equal to no. Okay, option B is the correct. The quantity of heat needed to raise the temperature of a body by 1 Kelvin is the body's specific heat capacity, latent heat fission. Specific heat capacity talks about the quantity of heat needed to raise the temperature of a unit mass of the body by 1 Kelvin. So a unit mass of the body was not cited in the question, so option A is wrong. Latent heat of fusion is the quantity of heat needed to change the state from its solid to liquid, or from liquid to solid without changing temperature, so it's not correct. So heat capacity is the quantity of heat needed to raise the temperature of a body by 1 Kelvin, and option C is correct one. Internal energy of a body is just the quantity of heat of a body, so option C is correct. The melting point of a substance is equivalent to its, the melting point of a body is equivalent to its liquidification temperature, when we talk about liquidification temperature is not about melting. Yes, it's also melting. When something is melting, it's turning to water. So it's equivalent. It's equivalent. This question is saying the same thing that happens to melting will also happen to, it's not solidification pressure, because anything pressure is out of this option. Vapor pressure is not correct. It is between A and B. It's the same thing. When we talk about equivalent, this is very tricky. This question, they say the melting point of a substance is equivalent. When we talk about equivalence, they are not the same thing as equation. So if it says it's the same thing as, so I can consider it, but now I will pick solidification temperature. So the option D is in for me. The temperature at which the water vapor present in the air is just sufficient to saturate the air is. The option should be no saturation point. No saturation point. Saturation point, I don't know, but when we talk about saturation point, we are talking about the point, when we talk about mostly point in heat energy, is the temperature. So temperature, saturation temperature, no, it's not. Dew point, yes, dew point is correct. Because dew point is the temperature at which just the definition we have here is the definition for dew point. So dew point is in for me. But when you talk about boiling point, is the temperature at which the atmospheric pressure is equal to the vapor pressure. While ice point is the temperature of a melting ice at a normal atmospheric pressure. So option B is the best for me. Heat transfer by convection is a liquid. In a liquid is due to variation of density of the liquid. Variation of density of the liquid. One variation of density, yeah. Expansion of the liquid as it is heated, no. Let me look for something that is more, let's go again. Latent heat of vaporization of the liquid, no. When we talk about vaporization, latent heat of vaporization, the quantity of heat that will make a liquid to change into vapor, no, so it's not there. Increased vibration of the molecule of the liquid about their mean point. When increased vibration of molecules of a liquid about its midpoint, talks about application of heat to a body. So the vibration between the molecules of that substance will increase, especially in solid. Expansion of liquid as it is heated. Yeah, of course, the liquid will be expanded, but is it the reason why we will talk about convection? Because convection is the actual movement of the heated particle from a higher so my option is A. That is in for me. Because variation of density of a liquid, yes. Because when it is heated, just like the ice, when ice when water is melting, the density is changing. So I will go with the variation or change of density. That's in for me. The distance between two successive crests of a wave is 15 cm and the velocity 300 meters per second. Calculate the frequency. Now, this question is not, now we have cm, 15 cm and we are having meter. So we have to do a conversion. We have to convert cm to meter before we think of what to do. And when we talk about the distance between two successive crests, according to our textbook, that is the definition given to a wavelength. So I think that is the wavelength. This is wavelength, is the distance between two successive crests of a transverse wave, and that is 15 cm. I have to convert it to meter by dividing it by 100, so I'm having 0.15 meters. And the relationship between the volume, frequency, and wavelength is the speed of a wave, which is this formula. And V is given as 300 is equal to, I'm looking for frequency, times the wavelength, which is 0.15. So this is going to be 300 divided by 15 over 100, which is 300 divided by 15. And this is 2. So 2000 hertz is the option. So I'm having 2000 hertz. So, and the option, you know, remember 2000 hertz is something as 2 times 10 raised to the power 3. It's not this one. Okay, that's option A for me. A boy receives the echo of his clap reflected by a nearby hill 0.8 seconds later. How far is he from the hill? Speed of the sound in air is 340 meters per second. When we talk about echo, echo is a reflection of sound, whose speed is 2 times the distance of the source of sound divided by time. V is equal to 2x over time. This is the formula for calculating the speed of sound in terms of echo, where x is the distance between the source of sound and the reflecting surface. So V is given as 340 is equal to 2 multiplied by x. I am looking for the distance all over 0.8. The time is 0.8. So what I'm going to do is 2x is equal to 340 times 8 over 10. This cancels this. You have that x is equal to 34 times 8 times 1 over 2. This times this is 4. X is equal to 16, write 6, carry 1. 12 plus 1, 136 meters. So 136 meter is option A, 27. The diagram above shows a stationary wave of wavelength 40 cm in a closed tube. The length of the resonating air column is, okay? Now, one thing we must know is this. I have node, and antinode. So we have node, antinode, node, antinode. So I'm going to have from node to node is half, which is half of the wavelength. And then from node to antinode is 1 over 4. What I'm saying is this. You know, this is caused by interference. So this is what happened. This is the first node. And the point when there is no meeting is called the antinode. So this comes here. All right, so this is node. Then there is antinode here, then another node. So from node to antinode is 1 over 2 wavelength. Then from node to antinode is 1 over 4 of the wavelength. So now, for us to get from the beginning to the end of the tube or column, we are going to have that the length is equal to 1 over 4 lambda plus 1 over 2 lambda, which is going to be, the LCM is 4, this is lambda plus 2 lambda, which is going to be 3 lambda over 4. So the length, which is also 40 cm, is the same thing as 3 lambda over 4. Therefore, I'm going to say that 40, now let's find what the lambda is, by the way. What is 1 lambda? Now the diagram above shows a stationary wave of wavelength. Good. The lambda is the wavelength and the wavelength is 40. So what we are going to do now is that 3 over 4 times, instead of lambda, I put 40. 4 into this is 10. 30 times 10. 3 times 10 is 30 cm. And that is the length given. And the option is B. An object is placed 10 cm from a pinhole camera of length 25 cm. Calculate the linear magnification. So if this is a box, the camera, this is just a camera, for example. They just make it look like one. They remember that this part is the screen. Then this is the pinhole. assuming I place the object here, which is, according to this question, an object is placed 10 meters. Okay, this is 10 meters. Now they say from a pinhole camera of length 25. A pinhole camera of length 25. The length is 25. That means from this pinhole, remember from here to here is height, so the length is from here to here, and that represents the image distance, which is 25 cm, all right? And that is V. So then from here to the pinhole represent the U. And remember that the magnification is V over U, and V is 25 divided by 100 all over 10. Why do I divide by 100? Because 25 cm must be converted to meter, because the U is also given in meter, and magnification does not have units. Therefore, this is going to be 0.25 all over 10, and then the magnification is going to be 0.025, and that is something as 2.5 times 10 raised to the power minus 2. Yes, 0.025. 2.5 times 10 raised to the power minus 2. So minus 2 option is D, and that is option. The focal length of a concave mirror is 2 cm. If an object is placed 8 cm from it, the image is at. All right. Now, this is a concave mirror. This is a concave mirror. All right. In this concave mirror, this is the principal axis, and this is the pole. And the focal length is 2 cm. And the object is placed at 8 cm at this point. That is, the object is placed at this point, 8 cm. That means the object, the image that will be formed is going to be a real image. It's not going to be a visual image. So what is, and it's going to be formed in front of this mirror. It's not going to form behind. If it forms behind, then it is a visual image. If it's a real image, it must form somewhere here. So we don't know the place it is formed, whether it is formed here or here or here. So that is what we are looking for. Now the object distance from this distance to this place is U. And then from here to here is F, which is the focal length. And we are looking for V. What's the distance for V? And then remember that this place is going to be 2F. So this is actually beyond F. If you now know the position of the object in front of a concave mirror and what will be forming. So at this point, I'm going to use 1 over F is equal to 1 over V plus 1 over U. I know F, and this implies that 1 over F is 2 is equal to 1 over V is what I don't know, plus 1 over U is 8. Therefore, V, 1 over V. Now, at this point, which principle am I going to use? Real is positive is what I'm going to use. Real image, because the image form is going to be real, and the object is also real. So I'm going to use real is positive. I'm not going to use new Cartesian. I'm not using new Cartesian, I'm using real is positive. So that is why my values are also positive. And even the options are also positive. All right, so V is equal to 1 over 2 minus 1 over 8. If I take my LCM, I'm going to have 8V. So this is going to be 8V all over 1 over V is equal to 8V all over 1 over 2 minus 8V all over 1 over 8. This cancels this. Sorry, let me continue here. I have 8 is equal to, this is 4V, and this is V minus V. 4V minus V. So I have 3V equal to 8. Therefore, 8 divided by 3 is equal to V. And what option is best for that? I is going to be 2.7. 2.7 because 8 divided by 3 is 2.6. I don't have 2.6 there. There's no 2.6 here. 2.7, 2.5. I'll go with 2.7. In a compound microscope, when we talk about a compound microscope, we are talking about a way of enlarging the image formed when you are using a microscope. Now, it comprises of 2 lenses of short focal length. So I'm going to go with short. In a compound microscope, the objective and the eyepiece lens are short. Yes, they are all short. Now, when a telescope is at normal use, the final image is at, 2 things happen whenever a telescope is at normal use. There is a point of coincidence between the focal length of the objective lens and that of eyepiece lens. So in that case, and that is not what they want to know here. Another one is that is at infinity because the image is at a distant object. So the image is at infinity is my option. A negatively charged rod is brought near the cap of a charged gold leaf electroscope, which has a positive charge. The leaf. All right, let's look at when a negatively charged rod, yes, it's negative charge, is brought near the cap of a charged gold leaf. Okay, good. Now, the gold leaf is already positive and the negative is coming. So if the gold leaf is positive, that means the leaf is going to be open with a positive charge. So it's going to collapse. Collapses and diverges. Diverges remains the same. It can never remain the same. It cannot collapse and diverge. There is no option like that. Diverges, no. It diverges when they are of the same charge. So it's going to collapse. So the option is D. The charge is stored in a 0.1 Faraday capacitor when a 10-volt supply is connected across it. All right. At this point, you are looking at capacitor, and the quantity of charge is directly proportional to the voltage connected across it, whereby quantity of charge is equal to CV, where C is the constant. Okay, so now with this, there is this value called the constant, which is also called capacitance. And remember that V is directly proportional to I, so that V is equal to IR. Yeah, this is a constant for Ohm's law. This is charge. Therefore, in this case, we are not given quantity of charge. We are looking for the charge. So Q is equal to C. C is measured in farad. That is capital F, which is called Faraday. So this is 0.1 times V is 10, and Q is 1 coulomb. When we talk about coulomb, that is the name of a man that explains better about the quantity of charge. So coulomb, that is why we are having C. So the option is 1. A capacitor, calculate the effective capacitor or capacitance of the circuit above. When we talk about a capacitor, the derivative of the effective capacitance, when it was made, it was opposite that of resistance. So when they are, if it is resistance, we are going to say these are in parallel. So we are going to take 1 over 2 plus 1 over 2 plus 1 over equal to 1 over R, but it's opposite to that of capacitance. So this is going to be added. They are in parallel, though they are going to be added. So the total I'm going to have there is 6 microfarad. Then the next one, this one is going to be 2 microfarad. Then the next one is 2 microfarad. So in this case, they are all now in series. So whenever you are doing series for a capacitor, we now do it as if you are doing parallel for that of resistance. Therefore, I'm going to have 1 over C is going to be 1 over 6 plus 1 over 2 plus 1 over 2. LCM is 6C. So 6C bracket 1 over C is equal to 6c bracket 1 over 6 plus 6c bracket 1 over 2 plus 6c 1 over 2. So this is 6 is equal to c plus 3c plus 3c. So everything is going to be 7c. So let me finish it here. 7c is equal to 6. Therefore, 6 is equal to 6 over 7. And that is going to be high value of 0. And that's going to be probably 0.8 and 0.8 or 0.9, and which is going to be approximately 1. So I'll be choosing D as my option. The maximum power transfer occurs in a cell when the external resistance is, okay, when we talk about maximum power, we're talking about the quantity of energy per time distributed by a cell or a battery. And when can that happen? Remember that the value of voltage or power or energy of electricity distributed is as a result of the internal resistance. That is why your car battery can carry some energy, can even power your television. And some other, like your dry cell, like the one you use for torchlight batteries, those ones cannot power a television because of the internal resistance. Now, if the internal resistance is very high, the battery will not give out much power or energy. So, but imagine when they are the same. So let's look at the options. The greater than the internal resistance, it can never be greater than internal resistance and still have an effective power transfer or distribution. Less than the internal resistance, it must be the same. Twice, no? The option D, the same at the internal resistance of the cell. And that is when the maximum transfer occurs in a cell or a battery. In a cell. So option D is best. If a metal wire is 4 meters long and the cross-sectional area is 0.8 millimeters square and has a resistance of 6 ohms, find the resistivity of the wire. When we talk about resistivity, now for a wire, many things happen for a wire. Resistance of a wire is directly proportional to length, and the resistance of a wire is inversely proportional to the area. So when I combine this, I have K L over A, such that K is given as rho. This value is another symbol, scientific symbol used for representing the constant of a wire or the nature of a wire, which is called resistivity. So I will remove this and put that as resistivity. And that is what we are asked to find. So the length is 4 meters, L is 4 meters, A is, wow, this question. Now, we have millimeter and we have meter. We must convert them. And the options are in meter. So you must convert this to meters before you can start solving. So first, I'm going to say that 1,000 millimeter make 1 meter. So I will find millimeter square. To find millimeter square, I have to square both sides. I'm going to square both sides. When I square both sides, I have that 10 raised to the power 3 times 2 and millimeter square is equal to 1 meter square. All right? So that means 10 raised to the power 6 millimeter square is equal to 1 meter square. Therefore, 1 millimeter square is equal to 1 over 10 raised to the power 6 meter square. So I have converted from 1 millimeter square is 1 over 1 million meter square. Therefore, if I have 0.8, I'm going to have 0.8 times. Instead of 1 millimeter, I will put 1 over 10 raised to the power 6 meter square. And, okay, that's going to be 8 times 10 raised to the power minus 5 meter square. In standard form, just using standard form. So this is the area. I'm going to use this value as my area as I continue to solve. conversion is very necessary. All right, so the area is now 8 times 10 raised to the power minus 5 minus 1. No, should be minus 7. Yes, it's minus 7. So I will have that the ohms, the R is 6. So I'm going to say 6 is equal to resistivity times 4 all over 8 times 10 raised to the power minus 6, minus 7, pardon. So this is going to be is equal to 6 times 8 times 10 raised to the power minus 7 divided by 4. This cancel, this is 2, this is 12. It's going to be 12 times 10 raised to the power minus 7, or 1.2 times 10 raised to the power minus 6 ohm meter. 1.6 times 10 raised to the power minus 6 ohm meter. Correct. That is option A. A circuit has a resistance of 200 ohms. The resistance of the circuit can be reduced to 120. Is that watt? No, it can't be watt. It should be ohm. When, okay, this question is saying that a circuit has a resistance of 200 ohms. It said the resistance of the circuit can be reduced to. All right. The resistance of the circuit can be reduced to. So when what happens? Okay. So in order to reduce a resistance, is either you. So first of all, we are going to find which one is effective resistance. The resistance of the circuit can be reduced to. So I'm going to say 200. So the effective resistance, because he said that circuit has 200 already. So I'm going to have 1 over R effective. I'm calling it RE. It's going to be equal to 1 over R1 plus 1 over R2, 1 over R raised to the power n. Good. Now, I'm going to apply 1 over 200 is equal to 1 over 120 plus, there is a new resistance which we are looking for. I am using parallel because I know that it is only parallel circuit can reduce a resistance. That's why I'm applying this. I'm not using series. So this is 1 over R. Yes. So I'm going to find the LCM, clear this fraction and find the value of R. Then I will make my choice. So if I find the LCM of 200 and 120, 200, 120, 2, that's 100, 60, 250, 30, 225, 15, and 3, 25, 5, then 25. Okay, so I have 8 times 3 times 8 times 3 and 24 times 5. So 24 times 25, which is 600 R. Okay, so my LCM is 600 R. So I'm going to have 600 R 1 over 200 multiplied by this equal to 600 R multiplied by 1 over 120 plus 600 R multiplied by 1 over R. All right, this cancels this. I have 300 R, then which is equal to 120 into this 12, which is going to be 5. Yes. 600 divided by 120. Oh, 5, correct. So this is 5R plus 600. So we have 300R minus 5R equal to 600. So this is going to be 295. So 600 divided by 295. Wow, good. So this is 3. This is 3. This is 3R. And this is 3R. So this is going to be 2 minus 2R equals 600. So R is going to be minus 1. 600 is going to be 150. That is 150 ohms. So the value there we have is A. Option A is 150 ohms and in parallel. So I'm choosing that even though this negative. All right, I'll work with option A. Now, PHCN, Power Holding Company, probably Nigeria, measures electricity energy in kilowatt hour. That is not, that one is kilowatt hour. What is the best method of demagnetizing a steel bar magnet? A steel bar magnet. Rough handling it, hammering it, beating it. The best method, when you use a solenoid, when you put it in a solenoid, it can be demagnetized. I will pick solenoid. The magnitude of the angle of dip, the magnitude of the angle of dip at the equator. At the poles, they are 90 degrees. At the equator is 0. So it's 0 at the equator. Yeah. Now, the diagram below, use the diagram below to answer the questions that follows. This is the input and this is the output. The diagram above is that of a step down. No, it can't be a step down because this is the output. An auto transformer, no. An oil transformer, no. A step-up transformer. I'm going to choose a step-up transformer because the coils are many in the output. So this is the secondary output and this is the primary. So step-up transformer is my take. The electromotive force in the secondary winding is, this is the secondary winding. It's reducing, it can't be reducing, it should be stepping up, so that is going to be increasing. It's going to be increasing. It's not going to reduce, neither is stabilizing. It's not going to be, I would prefer increasing. Varying, I won't choose varying because I'm not talking about magnetic, Faraday's law of electromagnetism. So I will choose increasing. The type of reaction is represented by the equation, yes, 2x1 and release of energy. Okay, what type of reaction? In this case now, I'm going to choose, look at 2 smaller nuclei combined to form 3. Yes, so I'm going to, and whenever there is a combination of 2 or more smaller elements to forming a bigger one, or nuclei of a particular element, we now talk about fission. So fission is that, it's not chain, it's not a chain reaction where there is a release of a neutron. Neither is there ionization, so it's not going to be fission, rather it's fusion. So option D is my best because it has to do with combining the nuclei of a smaller element to forming a big one with the release of energy. When an atom undergoes a beta decay, the atomic number of the nucleus increases by 1. Whenever there is, let me show you. Remember that a beta decay goes with this. All right, so because of -1, so because of this -1, to balance the equation, you add. Let me take you back a little to this one. If I have, let's assume that I have, let me just use one like, let's say 50. Okay, let me just use 50 x3, then plus this. Then we give you. Now, because you have to balance whatever you have here, plus probably an energy release. Because you have to balance here. This plus 0 is still going to be 50. Then this one now, 3 minus is going to be 4. So there is an addition of this element, of the atom of this element. So because it's an addition, it's increasing by 1. So I'm going to choose increase by 1. It can be 0, It can't remain unchanged. It can't decrease. It's going to increase by 1. So the value will increase by 1. All right, calculate the mass of copper deposited during electrolysis when a current of 4 ampere passed through a copper salt for 2 hours. ECE, that is electrochemical equivalent of copper, which is represented as Z, is equal to 3.3 times 10 raised to the minus 7 kilogram per coulomb. This question has to do with Faraday's law of electrolysis, the first one, which says that the mass deposited is directly proportional to the quantity of electricity which passed within that range of time. And is given as M is equal to IZT, or whatever they like to call it. It's just IZT multiplied in each other. So in that case, I represent the current, which is 4. So the mass is going to be 4 times Z is also given as 3.3 times 10 raised to the minus 7. 3.3 times 10 raised to the minus 7 kilogram per coulomb multiplied by the time is 2 times 60 times 60. Because it is in hour, to convert from hour to seconds, you multiply by 336,600, which is 60 times 60. So 4 times 3.3 times 2 times 60 times 60, which is 95040. Mass is 95040 times 10 raised to the minus 7. All right, so the options I have, this is 9.5, so we have to convert this to standard form again. So I have M is 9.50 times 10 raised to the power. I just left this ones, not because of anything, just let me do with 1 decimal place. 1, 2, 3, 4. So this is 4 on top times 10 raised to the power 7 minus, and it's going to be in kilogram. 4 minus 7 is minus 3. So M is going to be 9.50 times 10 raised to the power minus 3 kilogram. So the option there is A. Which gas produces a pink colored light in a discharge tube? When we talk about electric discharge tube, we are talking about a setup whereby a gas can conduct electricity with a cathode and anode at both ends and a very low pressure in the tube using a vacuum pump and a very high potential difference between the tube, between the anode and cathode. So the kind of gas that we produce a pink colored one, it can be argon, because the argon produces a different color. It's not pink, it's not neon. So I'll choose air. Air is the gas that can produce a pink color in a discharge tube. Now, when 210 lead atomic mass and lead of 82 atomic number decays to 206, or another isotope of 206 of atomic mass, 206 and atomic number of 80, it emits. Now look at this. It is reducing. 210 minus 4 will give you 206, and 82 minus 2 will give you this. And the only element that can cause that is a helium. Helium is 4, 2. All right, it's 4, 2. So, and that is an alpha particle. No, it can be 2 alpha particle and 1. It can be alpha particle and beta, and alpha particle. Yes, an alpha particle is the right option. It's not beta. When we talk about beta, we are talking about 0, minus 1. This is an electron, which is also regarded as alpha particle. A common emitter configuration. In a common emitter configuration, the output voltage is through the, this is a kind of diode, a triode, a kind of, with 3 legs, which is the base, emitter, and the collector. So in such an arrangement, the output voltage is through collector. Yes, it's not the emitter, because it has 3 legs. It's not through the emitter. it's not a base, it's not a resistor, so I will go with collector. Now, which of the graph below shows the characteristics of IV transistor? When we talk about characteristics of the IV transistor, that is I on the vertical and V on the horizontal. And it's not this straight line, it's not this curve, it's not this kind, even this and this are the same. So the option is this. We have come to the end of this class. You can practice more past questions using the ExamGuide app. See you in the next class. Bye-bye.